Hello, and thank you for attending today's Advanced Weather Spotter training for the Inland Northwest. My name is Lori, and I work at the National Weather Service office in Spokane. So the objectives of this talk today is to help you guys understand your roles that you play as a weather spotter for our region, to describe the threats, the weather threats that we see across the Inland Northwest, and to help define the kind of what we're looking for in spotter reports, and also just to give you guys a little bit more detailed background about the basic structure of thunderstorms and severe thunderstorms as well, and how to keep you guys safe during severe weather as well. So first things first is we're going to take a look back at last year and our severe weather we had last summer. The first thing was just about a year ago, May 6th, we had wind and tornado damage. The tornado touched down on the West Plains and then lifted up and then traveled across downtown Spokane and then came back down right near where the city and valley city limits kind of are right together near each other, just south of I-90, basically near Sprague. So you can see the damage from that, overturning a trailer, moving a boat, hacking trees, 40, 50 feet up the tree line. We also had flash flooding on July 4th in Concanoli, and that was a result of very heavy rainfall in a short amount of time. And you can see the big picture is a house that was being remodeled or redone, I believe. But you can just kind of see the force of when you have thick, heavy rock and mud and debris flowing quickly towards you. It's really surprising. It's really surprising how quickly that stuff moves, just huge boulders and rocks moving, or the fact that it can push vehicles and houses, given the how much rain occurs over a short amount of time. We also had large hail August 11th. That storm started in southern Spokane County. It did some pretty significant damage in Rockford, significant damage in their cemetery, but also to trees as you're coming into town and at the city park there. And then it moved into Otis Orchards and the Newman Lake region, where it dropped significant hail that we don't typically see this in this area. I would say the last time we saw hail this size was probably 2007 or 2008, I believe. So it's not hail that you see every year, that's for sure. But we easily had hail 2 inches or slightly bigger with that storm. And it did produce a significant amount of damage just because it went over such a populated area of Eastern Washington. So let's talk about our office. So the Spokane Weather Forecast Office forecasts for Eastern Washington and North Idaho. That's from the Cascade Crest to the Idaho-Montana border. And it includes 13 counties in Eastern Washington and 8 in North Idaho. And our elevations range from about 170 feet along the Columbia River to up above 9,000 feet in the Cascades. And you can see where all the weather forecast offices are in the United States. We have about 133 offices. And that includes Alaska, Hawaii, Guam, and Puerto Rico. And this map here just kind of shows you, we don't break up our forecast necessarily by counties. We break up our forecast by what is called zones. And so this map kind of outlines to you what our zones look like. And it's kind of more by like geographical area. So this is kind of the Palouse. This is the Idaho Palouse. This is the Upper Columbia Basin. This is the Moses Lake area. This is the Waterville Plateau. So it's kind of more based on geography and the weather that you would see in that particular zone. So let's talk about some of our tools we have. Some of our tools that we have online or that are available for you guys to look at or use or see. The first one is our radar, and that is right outside our front door at our office. Big golf ball or volleyball or soccer ball in the sky. And the cool thing about our radar is instead of, it used to just look at the particle in the cloud just in the horizontal, but now it's called dual pole. Now with dual pole, we can look at it vertically as well. And so that helps us identify what is in the cloud, whether that be a raindrop, whether that be snowflakes, whether that be hail. And that helps differentiate for us what is in the storm. The other thing that radar, we have reflectivity, which is what you guys normally see, for example, when you probably watch the weather report on TV. But there's also velocity, and that's this here. And the red velocities mean it's moving away from the radar, and the green velocities mean it's moving towards the radar. So you need to know where the radar is in order to figure out if there's, for example, if there's rotation in a thunderstorm. We also have our weather balloon that produces SKU-T log P charts, which is this image here that shows the temperature and dew point. So we release our balloon twice a day, every day. Currently, it is done at 4 p.m. and 4 a.m. There's about 92 sites in the United States that does it, but across the whole world, balloons are released at the same time. So when I released the balloon this afternoon at 4 o'clock, there were Miami was releasing a balloon, and New York was releasing a balloon, and Detroit was releasing a balloon, as well as London was releasing a balloon, and Sydney, Australia was releasing a balloon. So all over the world, in South America and Africa and Europe, balloons all were being released at the same time. And that kind of helps give us a snapshot of what is occurring. And all that data from all the balloons is put into our weather models, whether it be the American model, the European model, the Canadian model. All those radiosonde data is put into our weather models to help us come up with our forecasts. And the balloon takes about an hour and 45 minutes to 2 hours. It goes about 100,000 feet, anywhere from 18 to 20 miles up. And given the sparse population of Eastern Washington and North Idaho, we typically do not get our radiosondes back. And in fact, this picture here is what the radiosonde looks like now. And this has changed in the last year or so. We continue to downsize and have smaller and smaller radiosondes, so we're not using as much material in our radiosondes. And most of them are not found because, you know, we aren't populated, and it probably just falls into the forest, etc. And in fact, you don't mail them back anymore because they figured with it being as small as it isn't worth mailing back and refurbishing them anymore. When they were bigger, it was worth it to do it, but not anymore. So you don't even have to mail them back anymore if you find them. And if you want to see more soundings like this is a website you can use to look at radiosondes, or I'm sorry, the SKU-Ts. So looking at weather satellites, we have a GOES-18 satellite, and it provides 16 different channels. We have infrared, water vapor, and visible. The infrared looks at the temperatures of the clouds, whereas the water vapor looks at the water content in the atmosphere fairly high up. And then we have the visible. The visible are these bottom three images. And the visible is great because there's a lot of different channels and you can see a lot of different things. So for example, this is showing you a fire off of the Southern California coast. This middle image, the thing circled here, that's a thunderstorm. That's an overshooting cumulonimbus cloud. So you can see that that's out of this whole picture, that is the strongest storm shown right now in that image. And then here's just a general image showing you the clouds. Now, across the Cascades and in parts of Idaho and western Montana, this is probably snow cover. You can even see it in the Olympics. So you have to kind of know how to read it, that, you know, if the clouds aren't moving, it could be cloud cover or it could be snow cover as well. But the nice thing about the satellite is we do get images now every 5 minutes. And if we believe that there could be strong or severe storms, we will ask, it's called for a mesosector, and that would be that they kind of move the satellite to an area where we could then get satellite imagery every 1 to 2 minutes. So if we're expecting severe storms, we can ask for that to be moved into our area so we have more frequent satellite images, which is pretty nice. Okay, talking about surface observations, most of the airports across the region have what is called an ASOS, which stands for Automated Surface Observing Station. And they are located on the runways, right where planes touch down, and they provide a plethora of data. You can get temperature, dew point, which then calculates the humidity. You can get wind speed, wind direction. You can get visibility, sea level pressure, precipitation, and weather occurring. And all that data is incredibly helpful for us. They're always on 24/7. A lot of our electronic staff will maintain or help maintain a lot of these stations. So we have them, for example, at Spokane Airport, at Felts Field, at Pappy Boeing in Coeur d'Alene, Sandpoint, Colville, Pullman, Lewiston, Moses Lake, Ephrata, Wenatchee, Omak, Winthrop. So those are some of the locations that we have these ASOS stations. We also use a lot of resources provided by like the DOT. So this is Spokane Region Traffic Management Center, and these are their cameras. And so we will use those to look at current conditions, whether it be cars slowing down because of hazardous driving conditions, or looking to see is it raining or snowing? Is the snow sticking to the road? Is it only sticking to the side of the road? What are the visibilities? Is there ponding of water on the road? So we'll use these cameras to help us a lot. And there are other cameras other than what's in the Spokane area, but the other cameras, like with the Idaho Transportation Department and the other Washington State Transportation Department, those aren't necessarily live stream, whereas these in the Spokane area are live streamed for us, but we still use the other cameras as well, like around the Columbia Basin to look for dust, or in Idaho to see if snow's accumulating on the Camas Prairie. So we do use a lot of cameras to help us make sure that our forecast is on track and that things are going according to our forecast. We do have supercomputers, and we do have high resolution models. So this top picture is just an image of what our supercomputers look like. So it's just a bunch of computers processing. I can't even imagine how much data it's processing and creating for us things like in these bottom images. So you can see here's just like a surface map of precipitation and pressure, just kind of giving us an idea of looks like something's moving into the BC coast, something is exiting off the East Coast, and we kind of have like high pressure in the central part of the United States. This is also something that is like a high resolution model, and all these models here are giving us like hourly data. So it's telling us hour by hour how it thinks the showers or thunderstorms or the winds or are progressing and moving through, or the instability. There's lots of different parameters we have to look at this stuff hourly, which is improving our forecast. So we need weather spotters. So maybe you're wondering why. Well, because as you can see here, this purple on the right-hand side of this image is the Spokane radar, and this pink on the left-hand side is the Seattle radar. And there is a lot of area right here, Waterville Plateau, parts of the Cascades, Okanagan Valley, even parts of the Columbia Basin, where we do not have very good radar coverage. And so it is important for people like you, our spotters, to kind of let us know what's going on so that we have real ground truth data to make sure our forecasts are on track. Maybe we need to make an update. Maybe we need to adjust something. Maybe you're seeing severe weather and we need to put out a warning. So that is just invaluable for us, especially like in the summertime when we have thunderstorms. We can see a little bit better than what this image kind of shows, because the thunderstorms are fairly, they extend vertically pretty high. You know, sometimes they'll be 15,000 feet vertical extent. And so the radar might be able to catch some of that, but especially in the wintertime when snow is falling out of a 2,000-foot cloud deck or a 3,000-foot cloud deck or even less, the radar completely overshoots that, and we can't see what is occurring across the central part of the state. So that's why it's so important for you guys to give us reports so that we know really what's going on. And you might think to yourself, well, I know my neighbor down the road reports, so like, why do I need to report? Well, things change in just short elevations or short distances, and it can change from rain to snow. It can change from freezing rain to rain, or from freezing rain to snow. So it is important. You guys do an important thing for us in helping us get ground truth and provide eyes on the sky for us for parts of the area that we might not be able to see. Okay, so I'm going to post a poll question here. So I think, make sure I'm doing this right. Here, oh, here. Okay, so why are weather spotters important? You guys can click on your computer screen and give the answer. Looks like about 80%, 85% of you voted. I do have some questions, so I'm going to answer them really quick. It is, when will this recording be online? No late, I would say probably, it's not me that's going to post it. It's going to be Robin. So when she has time, she will post it. But I would say within the next week or two at the most. If she works tomorrow, she can post it tomorrow, but I'm not certain of her work schedule. And then how much of North Idaho is covered by satellite? All of North Idaho is covered by satellite. If your question is how much of North Idaho is covered by radar, that's a little bit different. As far as North Idaho covered by radar, most of it is covered. It is a little bit difficult for us to see down towards southeast of Lewiston, so towards the Camas Prairie, Winchester, Nez Perce, Kamei. Missoula's radar is pretty high up. Their radar's actually located on top of a mountain, and so even for them to see parts of Idaho and Clearwater County can sometimes be difficult. So as you're getting towards Riggins and Grangeville, Orofino, sometimes those locations are difficult to see as well. But our office does know to use, there's times where using the Missoula radar is good. There's times when using the Pendleton radar is good. There's times using the Seattle radar is good for our crest of our Cascades. So we know that the coverage, where the coverage is challenging, and we adjust accordingly, and we'll sometimes use our surrounding offices' radars to help us see what's going on. Okay, I'm going to close the poll. And it looks like 94% of you said all of the above. A couple people said provide reports of ground truth on severe weather, which is true. But spotters are also important because they fill in the holes not seen, and they do add credibility to our warnings because you guys help verify our warnings with your reports, which I did not mention, but good job for you guys knowing that and answering that question. I appreciate that. All right, moving on, we're going to talk about weather hazards that change with the seasons. So for example, right now we're kind of dealing with river flooding as the snow begins to melt off the mountains. And especially you have to be careful if the snow melts too quickly. So if we get too warm too fast for too long, then it can definitely cause flooding across the rivers as they fill from the snow melt. And then we move into flash flooding season, which typically I would say is about June through August. And that's when you would see heavy amounts of rain in short durations of time. We also have fire weather, so we care about wind and dryness, how that would be carried, those conditions can carry fire. We also care about lightning and smoke, where the smoke is going, where there are fires. Like for example, we've been watching, we know that there's fires in Alberta right now. And so we've been watching the smoke forecast through the weekend to see if there's the chance of smoke moving in to the region. And it looks like there could be some haze, but it doesn't look like it's going to be a big push of smoke into our region. But that's something that we keep an eye on through the summer. We also care about thunderstorms. Right now, we're generally just seeing our typical spring storms where they pop up, put down some rain, some wind, some lightning, maybe some small hail, and then they typically dissipate fairly quickly. But as we progress through summer, we have more opportunity to see stronger storms and potentially severe storms. So that's something we watch out for. And then, of course, as we move out of fall is typically our quiet season, more or less. We will see wind storms in the fall, but and then we move into winter with snow and ice and freezing precipitation and rain and wind. And then we repeat the cycle all over again. So what's in a spotter report? Well, we just want you to tell us what's going on. Who, what, where, when the event began or ended. You can estimate the wind, speeds, and the size of the hail, and any damage or injury that you know of. And even if you're unsure, report it anyway, because just let us know you're unsure, and then we can maybe go dig in and try and find reports to clarify your uncertainty. And if you're traveling, feel free to send reports to us as well, because we can relay those to other offices, even if that's not nearby, we can do that as well. And there's lots of ways for you to submit reports, and some of them you wouldn't even need to necessarily let us know. You could just, for example, use MPing, and that'll work anywhere in the United States, and it would feed into that local forecast office's computer system to receive your report. And we'll talk about that in a minute. So poll question number 2. So what type of severe or hazardous weather do we not experience in the inland Northwest? All right, I'm going to close it. You guys are correct. The answer is hurricanes. Thank you for participating in that question. We do not typically see hurricanes. The reason being, you really need warm tropical waters for hurricanes, and the Pacific Ocean, as you move out of Southern California, the Pacific Ocean is incredibly cold. So cold waters kill hurricanes. So our Pacific Ocean is not warm enough to keep a hurricane, feeding a hurricane to live. So we don't see hurricanes in this part of the country. So how to report. So there's lots of different ways for you guys to report. You can call the 1-800 number and give us a report that way. And if you do, just tell us what you saw, where you are, and when it occurred, and we'll take it from there. There's lots of other ways to report. You can go to our webpage, and at the bottom of our webpage, you see all these little thumbnails. And this one here, that's highlighted in red, is submit a storm report, and you can click on that, and it pulls this up here on the left, and you can just pick what kind of storm report you'd like to report. And the nice thing about that is you submit it, and we get an alarm in our operations area, and we can click on it on our computer system and read your report. And the nice thing is it gets put in automatically into, if we were to do a storm report, like a local storm report, where it has, like, you know, the wind damage or the amount of precipitation we saw or the snow amounts, it automatically gets put into that software so that we don't have to put it in ourselves, which is kind of nice. You can also submit a report through social media. We are very active on Twitter and Facebook, and those accounts are monitored 24/7. I talked about MPing. I love MPing. The only thing I don't love about it, well, there's two things I don't love about it, but it is such a great way for you guys to send reports to us. It is an app on your phone. It was kind of created by the University of Oklahoma with NASA, and you can pull up the app, click, I want to submit a report, and then you can go in and say, it's raining, it's snowing, it's windy, I have tree damage, and then there's two bad things about it, in my opinion, at least. Number one is you can't say anything, like you can't type something in to add to what you're reporting. So that's a disadvantage. And number two is I can't acknowledge that I saw your report, but just know that when you submit it, it literally I have my radar up at my computer screen on my computer, and I can see your MPing report, and I can have a little cursor readout, and it reads out rain or, you know, small branch damage or, you know, that kind of stuff. So it is incredibly helpful. I use it all the time, and I used it yesterday actually when it was raining at my house. And the other thing that's actually kind of helpful, it's really funny, you know, when people are traveling. So sometimes I'll see people driving down 195 or people driving I-90 across the state, and they'll submit MPings throughout their travel. Hopefully they're not driving, but hopefully they're the passenger, but they're submitting MPings as they drive, you know, from one location to another, which is very helpful. I've done it before, like traveling just across Spokane, as, you know, for example, if you were to go up the South Hill and it changes from rain to snow, or you go up 5 Mile and it changes from rain to snow or something. I think it's helpful. You can also share your reports through our email address, nws.spokane@noaa.gov, and that is monitored 24/7 as well. And you can send us pictures of your reports. So emails are important. It's important for us to have your guys' email because, for example, if we're expecting potential widespread severe weather, we will send out an email to you guys to make you aware of it, so that if you see hazardous weather or you hear of something, you can call us and let us know. So we kind of give you guys a heads up a day ahead of time or the morning of, just to kind of let you know. We also do send out quarterly emails, and we do send out emails when, for example, we have spotter training, which is in the spring and the fall. So we don't spam you by any means, but we send out 6 to 9 emails maybe a year to you. So as a spotter, we may also contact you. So we can actually plot your location in our computer system. And so while we're watching the radar through our computer system, we can plot you and see if the storm is going directly over you, or is approaching you, or is going to miss you by a couple of miles. And so we might pick you out and try and call you. And we've done it already this year. I've called a couple of spotters a couple of weeks ago, where I thought that the heavier thunderstorm went over, it was kind of towards Valley Ford. And so I called some spotters to get verification of what was happening. Was there hail? Was it big? Was it breezy? Did the winds come? Was it just heavy rain, etc.? So we may call you if we think you're going to see or are experiencing the weather. So like I said, ground truth, you're helping provide ground truth, which is very helpful. Oh, we have a question about MPing. Let's see. Can you enable location so it automatically pulls that info? Yeah, it automatically knows where you are when you get on MPing. So, and the cool thing is if you use other radar apps, so for example, I use another radar app, and MPing actually gets put into that radar app. So I will be looking at the radar on this other app, and I can see your guys' MPing. So the other public can see your MPings as well, which is kind of cool. Can it attach photos? No, I do not think it can attach photos, but that's why social media and our email would be helpful. Can we email that we just sent an MPing? Yeah, you're more than welcome to email us at any time and let us know. But we do see them. We have our radar up constantly. So and it's automatically, MPings are automatically loaded on my radar images so that I can see them at all times. Okay, yeah, our email, we do have 2 emails. So on our webpage, there's a different email, but that is monitored as well. So you can use that. Our other email is nws.spokane@noaa.gov. So, but both of those are monitored 24/7. So you can email either account and we would see it. Okay, poll question number 3, here we come. What would be your preferred way to send reports to the National Weather Service? I'll give you a couple more seconds. Okay, I'm going to close it. Most of us have responded. It looks like 18% of you said call the office. 53%, oh, now it's 50% of you said send a report online. 11% of you said you would tweet or post it on Facebook. and 22% of you said you would email the office. So it's a wide variety. You know, it's what's convenient for you guys. You know, that's what's so nice about it. There's lots of options and to do it. So whatever is easier at the time for you. Okay, moving on. We're going to talk about thunderstorms. Okay, so there's some main ingredients that you need for a thunderstorm. And the main ingredients are moisture, lift, instability, and vertical wind shear. And we're going to talk about these in a little bit more detail. So the first ingredient you need is moisture. And moisture forms the clouds and the precipitation associated with the thunderstorms. And it's interesting, a typical cumulus cloud weighs, you guys are going to be shocked. How much do you think a cumulus cloud weighs? Just think about that for a second. A typical cumulus cloud weighs actually 1.1 million pounds. Isn't that crazy? I think that's just crazy. So our primary source in receiving moisture is from the Pacific Ocean. But in the summertime, what happens is there is high pressure that tends to form in the Four Corners region here, and high pressure rotates clockwise. So the high pressure is circling like this, and you will get moisture from the Gulf of California, or the Gulf here, and it will come up this high pressure and move up through California, Nevada, into Oregon, and after a day or two, we will see the increase in moisture in our region. And that is a big trigger. It's a big pattern recognition for us in seeing that moisture move up. Is we need to start looking at potential thunderstorms for our area. We are able to monitor that moisture via, for example, this bottom image is the water vapor satellite. So we can see it on that. We can monitor the soundings and how the soundings change from day to day, or from like a sounding in Oregon versus the sounding here. Where's the moisture? And terms that we will use a lot of times in our forecast discussions when we're talking about that is things like precipitable water. And precipitable water is the depth of water in a column of air. If all the water in the column was precipitated as rain. And then we talk about dew points. Dew points is the temperature at which the air has to be cooled to become saturated. So when the air cools to its dew point, you will see dew, or the water will condense at the surface. And then the other word we use a lot of times is relative humidity. And the humidity just tells us how much water vapor is in the air compared to how much it could hold at that temperature. Okay. Next ingredient is instability. So how the atmosphere mixes. And we talk a lot about unstable versus stable conditions. First, let's talk about neutral, which is this bottom middle picture here. And neutral is if you were to take a parcel of air and lift it up the mountain, when it gets to the top of the mountain, it's just going to stay at that elevation. That would be a neutral condition. A stable condition is you're taking that same parcel and you're pushing it up the mountain, and when it gets to the top of the mountain and starts to go back over the other side, it goes back down the other side of the mountain. So that is stable, and that happens constantly in the wintertime, but it does happen in the summer as well. And it's mostly because there's warm air above and cold air at the surface, and the warm air traps the cold air so that the parcel can't keep rising. And then we have stable conditions, or I'm sorry, we have unstable conditions. And that's when you take a parcel of air and you push it up a mountain, and when it gets to the top of the mountain, it keeps going up. The parcel will keep moving up and you create unstable conditions. So we can monitor instability by looking at soundings, by looking at surface observations, by looking at the weather models. Those are all things that show us the instability. And the terms that we would use perhaps in our forecast discussion are CAPE. And CAPE it stands for convective available potential energy. And that is the amount of fuel available to a developing thunderstorm. So you want a lot of CAPE if you want a good thunderstorm. Another word we use is lifted index, and that's just a stability index to measure the buoyancy of the atmosphere. And then we also use lapse rate, and lapse rate is the change in temperature with height. So how quickly temperatures change with height. Okay, William's question has, are thunderstorms in the Northwest pulse versus upper air sheared type? So yes, I would say most thunderstorms in the Pacific Northwest are pulse, and we're going to talk about the different types of thunderstorms, and pulse is going to be one of them. So we'll talk more about that. I think it's after this, talking about the ingredients. We'll talk about the types. So yes, that's a great question. Okay, moving on to ingredient number 3, we need a lifting mechanism, and that's something that forces the air upward. So for us, a lot of that is our terrain, that the parcel is moving up over a hill, over a mountain, the Blue Mountains, the Cascade Mountains, the Okanagan Mountains, Mount Spokane, lots of mountains, the Cabinet Mountains. There's lots and lots of mountains to pick from. So the mountains in the terrain, that parcel is forced up, so that could be a lifting mechanism, but also a cold front can be a lifting mechanism. So you can see in this bottom image here, it's a boundary. So here is the blue triangles is the front, is the cold front right here, and it's just the cold front, it's the difference between the two boundaries. So you've got the cold air behind it, you've got the warm air in front. Where they meet is the cold front. And air is forced up by a cold front. So that's why in the summertime, when you hear about a cold front coming through, again, pattern recognition, when that happens in the late afternoon or evening hours, we will typically see thunderstorms during that. They'll be, maybe a little bit more widespread across the region when it's a big cold front moving through, because you're getting lots of good lift, which is what we talked about. Not only from the cold front, but then from the mountains as well as it moves across the region. So we monitor that with satellite, radar, the soundings, surface observations. Terms that we would use in our forecast discussion would be vertical velocity, which is the upward motion in the boundary layer. And the boundary layer is just an area kind of in the vicinity of the surface. It's not directly the surface, it's kind of just above the surface. So it's the upward motion in that layer of the atmosphere. We talk a lot about vorticity. And vorticity is the rotational spin in the atmosphere. And then we talk about fronts. So, for example, a cold front or a warm front is a boundary between two different air masses. Does the Pacific Northwest, here's another question, does the Pacific Northwest get dry line thunderstorms? That's a good question. It's not necessarily, I'm going to have to process while I speak. So we don't necessarily have like a definitive dry line like you would necessarily see like in Texas, for example, where they have like blatant dry line between the moisture and the dry area. But we do get dry thunderstorms in our area where it's been so dry, and it's so dry, you know, from the surface to 5 or 8,000 feet, that even if thunderstorms form 10, 12, 15,000 feet up in the atmosphere, as the thunderstorm releases its rain or hail, it's encountering that incredibly dry air. And so the hail will melt or the rain will evaporate. And so that we do see dry thunderstorms in our area. And we see them, and we get them a lot. Sometimes we'll see them a lot at night when we get elevated thunderstorms that occur at night. Sometimes those can be dry with fairly significant lightning. I hope that answered your question. Okay, talking about wind shear. So wind shear is what you need to create the rotation in a thunderstorm if a thunderstorm is going to rotate. And it's just the change in wind speed and direction with height. So this image here on the right. So you can see at the bottom, the arrow is pointing and the wind speed is less. And then as you move up in height, typically the wind speed gets stronger. So that's what we mean by wind shear. And we can monitor that with the radar, with our soundings, with surface observations, you know, looking at observations in Colville, and then looking at observations in the mountains around Colville, for example. So the terms we would use for that are helicity. And helicity is a measure of the amount of rotation found in a storm's updraft. So amount of rotation found in a storm's updraft. And then there's shear, which we talked about, is the change of wind with height. And then a hodograph is a diagram that helps you see the movement of the parcel of air. So here's a picture of a hodograph. So it plots the wind, speed, and direction at several different heights. So you can see where the parcel is going as it's moving up in the atmosphere, which is helpful. Okay, thunderstorm basics. So here's a picture of a thunderstorm over the Rathdrum Mountains. And in this image here on the right is the updraft of the thunderstorm. So where the parcel of air is moving up, the storm is getting stronger. The cumulus base of the cloud it's typically rain-free. And that upward motion, that parcel of air that is condensing and creating the raindrop and is eventually getting high enough that maybe it's freezing and creating hail and lightning, that updraft can reach up to 100 miles an hour. And then you have down here the downdraft, and that's the dark part of the storm. That's where rain is falling. That's where your hail is happening. That is where you would see a shelf cloud as well from the thunderstorm. Okay. So what is a severe thunderstorm? So what categorizes a severe thunderstorm in our area is winds greater than or equal to 58 miles an hour or wind damage, and hail 1 inch or greater, or a tornado. We would issue a tornado warning for that. So less than 10% of thunderstorms are actually severe. And even though lightning is always present in thunderstorms and is very dangerous, the amount of lightning that you see in a storm does not make a storm severe. It is based off of the winds and the hail, and if there is rotation in the storm, and we think that there is a funnel cloud forming that could reach the ground. Okay, so let's talk about, well, here, I think I've got some questions. Does Doppler radar have a height limit? For example, will it reflect from the surface up to 2 or 3 kilometers? Okay, so the radar, the way the radar works is it scans at different elevations. So it'll scan at 0.5 degree, 0.9 degree, 1.3, 1.9, etc. So in Spokane, the heights that you see from our radar are different than the heights you would see as you go further away from the radar. So for example, in the Camas Prairie area, the lowest elevation scan that it can see is like 12,000 feet of a storm. So that's why when it's snowing out of a 3,000 foot cloud deck, we can't necessarily see that on the radar, and we rely on cameras and weather station observations and reports from social media or spotters. So that's and it's the same for the Cascades. I think the Cascades we see about, I think Wenatchee we see at like 10,000 feet or so. So severe weather climatology. So by month, you can see that the biggest, climatologically speaking, the biggest months that we see wind and hail damage is in July. And typically, the best month climatologically to see tornadoes would be May. If we continue with very warm weather and a ridge, we probably will not see very many tornadoes this year. So, but if we do get a trough that moves in or a low that moves in, then we could definitely see some tornadoes. But it's the climatology of the month. So you need certain, you need that trough of low pressure or that low moving through to kind of create the rotation that we would typically see for tornadoes. But tornadoes here are so incredibly weak, and there's a slide coming up that'll show you that information that I can explain a little bit more. But the time of day, you can see there's a very pronounced, about 1 o'clock it starts to pick up, and it continues through the afternoon, and then by 9 o'clock it's decreasing pretty significantly. So we get some heating going in the morning, get some heating at the surface, get some clouds developing, and then it's really going by the afternoon. And then when the sun sets, part of the energy is lost with the daytime heating decreasing and it cooling down, and our threat of thunderstorms typically decrease. But like I said, you can get elevated thunderstorms at night, which don't really take into account surface heating, the sun heating the surface and creating unstable conditions kind of thing. Okay, question 4. What would be a good ingredient for thunderstorm development? High precipitable water, low dew points, high lifted index, high pressure. You guys are torn. You guys are still torn. Okay, so someone answered at least every choice. So yes, you want high precipitable water values. That definitely helps in the formation of thunderstorms because that's your moisture that you need. Low dew point that does not really help with thunderstorm development. So that would probably be a no. Lifted index, yes, you want to see a lifted index. The way we look at lifted index, it's actually we want to see a negative value. So like seeing a lifted index value of like 6 would not be good, but to see a lifted index value of -2, that would be good. And then high pressure, I think I know why those who chose high pressure, it's probably because you're thinking, I talked about the four corners high and how we can get moisture that streams up around that. And that is true. If that's something that that's pattern recognition that we keep an eye on, especially in the summer. But that's not, for like this time of year, it's typically not something that we're concerned about. And if there's high pressure specifically over the Pacific Northwest, like example, this weekend, we're not going to see thunderstorms from that high pressure in the direct vicinity of the Pacific Northwest or the inland Northwest. So I would say the best answer probably would be high precipitable water. Okay, next, moving on, we're going to talk about the different types of thunderstorms. Oh, that's so funny, you guys. I'm reading your responses. Okay, it's totally fine. You guys, it doesn't matter if you get it right or wrong. It's just something fun for us to do while I go through the presentation. So I'm not judging you and I'm not grading you and you're not going to get a score. So no worries. Is dew point, but someone asked, is dew point related to cool temperatures? So let's go over that again. So the dew point, for example, let's say right now outside it's 62 degrees and the dew point is 32 or something like that. Then you could calculate the relative humidity from that dew point. The lower the dew point, the bigger the spread between the dew point and the temperature, the drier it is. So if you have like a 50-degree temperature dew point spread, it is incredibly dry. Whereas if you have like a 5 or 6 degree dew point spread or even less, then it is moist, it is very moist out. The relative humidity is high. It's like 85% or higher. So good questions, you guys. Okay, so we're going to talk about the 3 main types of thunderstorms. Okay, single cell. So someone was asking about single cell, or do they call them something? Pop-up, pulse, yes. So single cell would be pulse thunderstorms. So you can see here the bottom image is kind of like the evolution of a thunderstorm. So you can see these updrafts, and the yellow here in the second part is the storm is kind of beginning to get strong. Here it's red. You can see there's a little overshooting cloud top at the top. You can see an anvil kind of developing here. And this is the strongest part of the storm. And now the updraft isn't able to sustain the thunderstorm. So now it's going to begin to drop its load. And so the thunderstorm will begin to drop its rain or hail to the region, and then it dissipates. So here is a video of that. And just watch now where kind of the thunderstorm base is. It's just above. You can kind of see the cumulus, the cauliflower-ness. It's just kind of above the cloud or the tree line. But as the video progresses, you'll kind of see how the cumulus clouds are kind of developing further up in the atmosphere. You're kind of getting that cauliflower cumulusness, but you can see it's already beginning to dissipate. They don't last very long. In this slide, it says they last less than 30 minutes, but here in the Pacific Northwest, they can last as little as 10 or 15 minutes. And they may contain some small hail and maybe some wind gusts to 30 miles an hour typically. There might be some stronger ones that might see gusts 35 to 40, but never anything severe from these kinds of storms. So some of these storms, these pulse kind of storms, you will get heavy rain. So heavy rain, downpours, and if you're going to submit a report about heavy rain, things that we take into account is if it's like a thunderstorm, we care about half an inch of rain in an hour. Whereas if it's like it rains all day, for example, we care about an inch in 12 hours or an inch and a half or more in 24 hours. And we actually had reports of an inch of rain in 12 hours. Gosh, what night was that? I'm trying to remember. I've worked a bunch of evening shifts and now I don't remember. But anyway, it was northeast of Sandpoint. Someone had called and said that they had like 96 hundredths of rain since 8 a.m. and they had said most of that had fallen in the previous 3 hours. So that was a good report. Like that was a helpful report for us to let us know what was going on. Okay, so hail. Lots of different sizes of hail. We can get lots of non-severe hail, but just a mass amount of accumulation of it, like this picture in Medellin. This is probably just falling out of a gutter or something, and that's why it's piling up there. But you can get it can cover the ground. Small hail can still do pretty significant damage to sensitive plants like roses or tulips or things like that as well. So, but you need a strong updraft to keep the ice growing. So in this bottom right image here, you can this is kind of an example of how hail forms. So what happens is this dotted line here is 32 degrees, and below it, you have raindrops. And the updraft is occurring in the thunderstorm, and so the raindrop gets pushed up into the thunderstorm and it freezes because it's below freezing here in the thunderstorm. But then because of it's cycling through, so it might get big enough where it starts to fall again down below the freezing line, and it will partially melt, or another raindrop will stick to the ice particle. So some raindrops are sticking to the ice particle as it melts below the freezing line, and then the updraft is strong enough that it gets pushed back up into the thunderstorm and freezes. And that's how the hail grows. That's why hail is not perfectly spherical. That's why it's kind of chunky looking, because it's getting, and you can kind of see like the layers sometimes in the hail because it's getting pushed up in a thunderstorm and frozen and then brought back down and thawed, and more water is sticking to the ice particle, and then it's getting thrown back up into the thunderstorm and growing. So that's why it kind of looks like it has layers on it. And then eventually the piece of the hailstone gets so big that the updraft can't support it anymore. And so that's when it falls out of the thunderstorm cloud and comes to the ground. So, and you can see here on the upper right image, just the different sizes of hail that we can see. So this was the hail last summer in Otis Orchard. So you can see the person was comparing it to the size of an egg. So comparing your hail to different things is very helpful. Like saying marble size hail isn't super helpful because marbles come in different sizes. So if you can compare it to a coin or something that is consistently the same size, a golf ball, a pool ball, a baseball, etc., that is what we would like to see. And remember, severe hail is over an inch, so a quarter or bigger. Okay, damaging winds. So we can get strong downbursts or straight line winds, and we'll talk about that when we talk about the next thunderstorm. They can be convective in nature, or they can just be for example, associated with a cold front or something. And it's important to report any damage you see from winds, or if you estimate anything over 40 miles an hour. And if you don't have a weather sensor at your house, you don't have to have one to estimate winds. You can use this chart on the right. It's called the Beaufort wind chart, and it just helps you estimate the wind speed if you don't have a sensor where you're at. But you can kind of see all the different kinds of damage that we can see. So like the April 27th, 2019, that was probably that could have been a thunderstorm, or it could have been a cold front. The windstorm of 2015 was a cold front. January 2021, I believe that was a cold front as well. So cold fronts can do a lot of damage in our area when they're incredibly strong. So severe winds is anything over 58 miles an hour. Okay, moving on to dust storms. We get our fair share of dust storms, and that is caused by prolonged dry conditions, very strong winds, for example, from a cold front, and then it coincides pretty significantly with farming practices. So when farmers are out tilling their fields preparing for planting, or when farmers have harvested after they finished harvesting, and the soil has been kind of worked and it's dry, and so the wind can come and just literally pick up that light fluffy dust and carry it. So you can see we have pictures of April dust storms. So that's April into early mid-May is kind of our dust storm season, and then mid-August through the beginning of September probably would be our other time period of seeing dust storms. But it produces a sudden reduction in visibility. And if you can give us intersections and roads of where the dust storms are occurring, that is helpful. And dust storms are also called haboobs. So these images of Harrington, those are haboobs. And you see that a lot. I know if you watch like the national news or something, you know, like the Phoenix area or Tucson in Arizona, or in Vegas, they can see big haboobs, and they have, you know, tall buildings that can see the haboobs coming in on their cameras and stuff. Okay, now we're going to talk about multi-cell thunderstorms. So the overall threat from these are, you know, you could have some wind and heavy rain, but the tornadic possibility is fairly low. And you could see some hail, but there's a better chance of probably seeing winds from these kinds of storms. So multi-cells form new updrafts along an edge, and they can last for hours at a time. So you can see here on the image, kind of in the middle, you start getting your towering queue, and then it develops, and these storms keep developing along, for example, a cold front or something. So here's a video of that. And you can see here the thunderstorm is kind of developing on the right side of the screen, but as we progress through, you can see lightning moving as the thunderstorm is moving, and several different thunderstorms developing across the region. So it's not just one storm, it's not just a pulse storm, it's several storms near each other with lots of new updrafts forming. Okay, Oh, sorry, I'm trying to do. Okay, so with a lot of these multi-cell thunderstorms, you'll see downbursts and straight line winds, and this is kind of an image on the right of what that looks like. So the rain will come or the winds will come down from the thunderstorm, from the downdraft, and it like pushes it hits the ground and just pushes out. And you can see microbursts, which are smaller areas affecting less than about 2.5 miles. And then there's macro bursts, which are bigger downbursts across the region. Okay. So someone asked, is the multi-cell the same as an MCS? So an MCS is just a convective complex of thunderstorms that becomes organized. So yes, I would say an MCS could be a multi-cell line of thunderstorms. And then someone asked, can you give a tutorial about how lightning is formed? Okay, I'll give you a quick tutorial. It's basically what you need in a thunderstorm for lightning to form is you need hail. You need ice particles in that thunderstorm because the ice and the thunderstorms will, and them moving about in the thunderstorm creates charge separation. And that's what you need for the thunderstorm to create, for the storm to create lightning, is you need that charge separation that you can only get when there's ice present or hail in the storm. Okay, moving on to flash flooding and flash flooding. Like I said, there's kind of different kinds of flooding. There's river flooding, just with rises on rivers. For example, this upper right one, the Palouse River, or just from either an ice jam or from snow melt with rain. Those are kinds of the things that we will see with river flooding. This was Pullman a couple years ago in the spring as well. And that was also contributed, not only was it snow melt, but it was they had very, very heavy rain that caused the Palouse River to flood in Pullman. But then we also have flash flooding, which is, for example, this from the Williams Flat Fire. I believe that was in Stevens County, or I think it was Stevens County. So that's where you get like very heavy rain in a short amount of time, and you're concerned about, for example, if the flash flooding is occurring over a mountain, the water not being able to, well, especially over burn scars. After a fire goes through, the ground is so charred from the fire, and it depends, and there's different burn severities depending on how quickly the fire moved through and how hot it was, etc. But there's teams that go in and survey that and look at that and figure that out. And after a fire goes through, the surface is just charred. And so when it rains, the soil becomes hydrophobic, and the rain cannot penetrate through the ground. And so when you get heavy rain over a burn scar, especially in terrain where there's mountains and valleys and things, you can see pretty significant flash flooding. And that's what happened here, was at the Williams Flat Fire. It was just very heavy rain late in the evening over the fire that had just gone through the area, and the ground was completely charred and the water could not penetrate into the ground. And so all that heavy rain created like an ashy dirt mess, and it just went down, and it just released and went down the hill. So that's something to be concerned about. There's also just flash flooding in urban areas too, you know, like there's been times when it's rained so hard in such a short amount of time, like for example in Wenatchee, that like the water pothole things that are on the streets, it was like shooting up because it was raining so hard in such a short amount of time that it overwhelmed the drainage system in Wenatchee, and they had pretty significant street flooding from that. So there's all different kinds of flooding that we see in our area. It's not just burn scars, and it's not just river flooding. There's all sorts of kinds of flooding that we have to be aware of in our region. Okay. This is a video. Oh. This is like a flash flood going down a river or stream from heavy rain. Okay. So there's also mud and debris flows, which are very similar to flash floods. And it's just heavy rain over steep terrain, and the rocks, it creates a soft ground, and the rocks are easily able to move down the slope. The rock, the mud, the debris, the logs, the twigs, whatever it is. And we see it all across our region. So from Wenatchee to Kamei, currently Bonaparte Creek has had issues because of a burn scar up there. They had quite issues last summer. They're even having issues now with the snow melting off the mountains and into the small streams and creeks in that area. And then this is another infamous area in Spokane, just past the TJ Minot Bridge as you head up towards Northwest Boulevard. Just that steep hill right there. There's a lot of times when rocks, if it's really heavy rain, the rocks will just push down the hill and onto the road. So let's talk about supercell thunderstorms. The deal with supercell thunderstorms is there is a rotating updraft. So that's kind of like the big difference with that. And the severe threat is high for everything. You're more likely to see hail, you're more likely to see heavy rain, wind, tornadoes, etc. So for example, on a radar, you might see this reflectivity, and here is the velocity showing. So for example, you need to know where the radar is. So in this image, the radar is to the right, on the right side of this image. So the green is going towards, let's see here. Oh, no, the radar is to the left. So the green is going towards the radar, and the red is going away from the radar. So that's how you get the counterclockwise rotation in this image. So with supercell thunderstorms, you'll see overshooting tops, which is this little thing at the top of this image in the middle. You'll get the cauliflower-shaped towers. You'll see a wall cloud, this image here down in Kamei, picture of a wall cloud. So you can kind of begin to see as you watch this wall cloud develop, maybe some rotation. And that's what you're looking for in a supercell thunderstorm, is that rotation. So we do get lots of reports of people thinking they see, for example, a funnel cloud or something like that. And so the main one I want to point out is the scud cloud. A lot of people will see scud clouds and think that they're funnel clouds, but they're not. They typically form out of stratiform precipitation, whereas, for example, the lower right image of a towering cumulus, that's what you really see funnel clouds forming out of. So the kinds of clouds that you would be concerned about in this kind of situation with strong thunderstorms would be towering cumulus. Mammatus clouds are indicative of very unstable conditions, and a wall cloud. Okay, moving on to tornadoes. Since we're running out of time, I'm going to go pretty quickly through these next couple things. It's a violently rotating column of air, but in order for it to be called a tornado, it must touch the ground. So, for example, in this picture in Spokane, you can't tell for certain if that is touching the ground. So that at that point, that image might be considered a funnel cloud. But in the picture for Airway Heights, and here in Spokane, July 2016, those you can tell they're touching the ground. And so those are considered tornadoes. So it has to touch the ground to be considered a tornado. Otherwise, it's just a funnel cloud. But typically, tornadoes in our area are less than 5 minutes on the ground. They're about 100 yards in diameter. They track about a quarter of a mile. They're very, very weak. They're mostly EF0s and EF1s. So this is that tornado that was in Airway Heights a couple years ago, and you can kind of see, you can see it on the ground. You can see stuff kind of moving up.
Right in the casino. I know. Look at that.
So that is an image of a tornado. I'm going to skip this because we're running low on time and just go to how tornadoes are measured or through the enhanced Fujita scale. And it's basically based off wind speed. If we can't figure out wind speed, we base it off of damage as well. But typically, we do not see very many tornadoes in our area. On average, Washington State sees maybe 2 a year. Maybe 2 a year. So as far as tracks across eastern Washington and North Idaho, since 1950 to 2017, you can see a lot of blue, which is EF0s. So blues and greens, EF0s to EF1s. We do see some 2s, and I do see 1, 3. That looks like it's kind of west of Davenport, and I do not know when that EF3 specifically was. I'd have to go back and look at some climatology, which I do not have available to me at this point in time. Okay, so talking about dust devils and funnel clouds. So, for example, the bottom 2 left images are dust devils. And a lot of times you'll see those and they'll form from the ground up. And a lot of times it's clear or mostly clear out, or there's no cloud near it. So that's how you kind of know it's a dust devil. And then funnel clouds, like I said, don't touch the ground. So if they're not touching the ground, they are not considered a tornado. But always call if you see a funnel cloud, because then we can look at it on our radar and see if we think it's going to continue to descend and touch the ground. Cold air funnels is what we see typically in May. That's our typical May tornado kind of scenario. Like I said, it's when you kind of get a cold spring weather system moving through is when we typically see these cold air funnels across our region. Okay, so I'm going to skip these questions just to keep moving forward. I'm sorry, you guys. I just want to be respectful of your time. So staying informed. So you can always check our website. There's also a Storm Prediction Center, and they put out a forecast for the general thunderstorm outlook. So the light green is general thunderstorms. A darker green would be marginal thunderstorms. And so they put out this forecast several times a day, and you can kind of keep afloat of what the national map shows of where the best threat for thunderstorms across the country are, and that's through the Storm Prediction Center. You can always go to our website. We put out the image on our website that you see when you first pull it up. We call those weather stories. So those, and you can scroll, you can click on, you can see there's different special avalanche bulletin, 70-degree climate stats, warming temperatures, cold water, spotter training. So you can click on those different quote unquote tabs and see the different pictures or weather stories we're trying to relay to you. But we also have, you can get to a lot of our forecast information based off of current hazards, radar, forecasts. You can look at the rivers and lakes. All that information is available on our website. And if you have questions or you're trying to find something, you guys are more than welcome to email us and we can walk you through it via email if there's something in specific you're looking for. Again, this is the bottom part of the front of our web page. And you can, for easy, quick links, you can click on the forecast discussion. You can look at our radar. You can look at observations and see if there's any kind of advisories or warnings out. You can submit a storm report. You can view storm reports. All that information is kind of available at the bottom with these kind of thumbnail images. You can get all this information. I'm gonna skip these. That's just information you can get off of our radar page images. But we can walk you, if you really want to look at that stuff, we can walk you through it at another time. Someone said College of DuPage weather. Yes, our office uses the College of DuPage weather website constantly. So that is a very good website that provides weather models and forecasts, and it shows you winds and heights and instability or precipitation type, or it is a very good and helpful web page to use if you'd like to use it. So another thing to note, if you're looking at our web page for things, sometimes we put things in UTC or Zulu time. It's not Pacific time, it's not Standard Time or Daylight Time. It's based off the time in Greenwich, England. And so, for example, right now, because we're in Pacific Standard Time, at midnight in England, it is 5 p.m. here. So when you hear us talk about, oh, it's 0Z, well, it's really 5 o'clock here, but it's midnight in England. So that's just some kind of information for you to know. So 0Z for us is in the evening, 12Z for us is in the morning. So if you're ever looking at these weather models and things online and you're like, well, why does it say 3Z? Well, 3Z right now is 8 p.m. for us. I'll do one more question. What are some useful radar products? So there's the reflectivity that kind of shows you the strength of the storm as it's developing. There's the velocity, which can show you winds coming out of the storm or if there's rotation in the storm. There's precipitation, so that can kind of give you an idea of how much rain is falling out of the storm. The radar can estimate the rain amounts as well. And then there's all of the above. So it looks like most of you responded and you picked all of the above. And that's a great answer. Thank you for participating. Okay, we want you guys to stay safe when you're giving your reports. So just, you know, we don't necessarily want you to go storm chasing because we know that that can be very dangerous. For example, some college students were killed while storm chasing in the plains, and we would never want that to happen. So if you're gonna go out and report the weather for us, we want you to do so in the safest of circumstances. We don't want you going out in the middle of a thunderstorm and getting struck by lightning. So we just ask that you use I know it's exciting and everyone wants to go out and look and do and see and report, but your guys' safety is always number one important to us. Lightning can strike as far as 10 miles away from a thunderstorm. So that's definitely something we want you to keep in mind, that even if you think the thunderstorm has passed, you know, you can still be struck. So that's why a lot of sporting events, you have to wait for 30 minutes after the last lightning strike or thunder was heard before you can continue on with your game. So gonna skip that. Just be aware of hydroplaning, which is heavy ponding of water on the roads. If you're driving fast, you know, it can literally like almost lift up your tires off the road and you can hydroplane and lose control of your car. So that's something to be cognizant of. Just being careful at night, especially with flooding, because you can't see and people just automatically think the road is there, and water is incredibly powerful. And with flooding, road can literally eat away a road. Flooding can eat water, and flooding, water moving, can eat away a road and you wouldn't even know it. And you can drive into flooded roadways and the road literally doesn't exist. And that you might think, oh, that doesn't happen here. It literally does happen here. Several years ago, we had some heavy rain in the spring, and I think it was in Adams County, rain, and it literally ate away a road, and the road, a big chunk of the road just disappeared. And it was over a hill too. So the car, we had pictures of it. You could see on the other side, like a car had to stop once it crested the hill because it looked, and the road just completely ended. Very, very dangerous. Stay out of damaged area just because of hazardous material and broken glass and metal and things where you can obviously hurt yourself. We don't want you to ever be put in a situation where you could be hurt, even if it's going out and surveying after the storm occurred. Okay, so here we'll do the last, I think this is the last question. So what would be a safe weather spotting scenario? All right, you guys, I like your answer. Staying inside during a storm, then looking for damage after, I should say, if it is safe to do so. You probably don't want to stand on a hill and watch an incoming thunderstorm, especially if you're outside exposed. You don't want to be the tallest thing, and you don't want to go hiding under a tree because then the tree is the tallest thing. So that is the best place to be in a thunderstorm is inside your house. And if you cannot be inside your house, then maybe inside a vehicle, not a soft-topped convertible car, but a hard-topped car, a vehicle. All right. So we're just going to spend the next 2 minutes going over the seasonal outlook. So far this year, you can see our temperatures. So from January through May 8th, our temperatures were at or below average for the large majority of the Western United States. We had a fairly cold winter. And then our precipitation percent of average, you can see for the most part, parts of Washington and Idaho and Western Montana were very dry. The exception to that would be parts of Douglas, Northern Grant, Eastern Okanagan, and Ferry County, where they did get a little bit more precipitation, which for them is very good because they have been very dry the last several years. So that was probably very welcomed for that part of the state. The seasonal outlook for the drought, you can see that on the image on the left, parts of eastern Washington, the Cascades, and the Idaho Panhandle are abnormally dry, and parts are even beginning to get into a moderate drought, a D1 scenario. And the forecast for now through the end of July is that the drought will likely persist. Where there is a D1 currently, it will likely persist, and drought conditions will probably develop across eastern Washington and North Idaho, because we're getting into our dry time of the year, and we probably will not see a lot of significant spring wet events from here on out. It's not to say that they won't happen. We could see a couple of days of cooler weather and some rain, but it wouldn't be enough to negate drought conditions. Our seasonal outlook for fire for June, right now it's looking good. Nothing, which we don't normally see a lot of fire activity in June. It would be like the Columbia Basin or like the fine fuels maybe beginning to dry out. But you can see in July, it starts to show something creeping up into the central part of the state. It's the Cascades. So the potential for some above normal wildfire activity for July. And then our seasonal outlook, our 8 to 14 day has above average and above average temperatures, below average precipitation. And I pulled up the 3 to 4 week. These are put out every Friday. And the 3 to 4 week, which takes us through the end of May and into the beginning of June, continues with the idea of above average temperatures and below average precipitation across our region. And looking at the summer as a whole, June, July, and August, you can see that it is saying above average temperatures on the left and below average precipitation, which I don't know if I can recall the last time we had a wet summer. So I think that's probably a good bet. And another thing to note is El Nino is coming. We are done with La Nina, and temperatures are beginning to warm in the equatorial Pacific, and the development of El Nino is likely. There's like I think it's like an 80% chance of it developing by the end of fall and continuing through the winter. Someone asked a question about Mammatus clouds. Mammatus clouds themselves do not produce funnel clouds, but Mammatus clouds are indicative of very unstable conditions where, like, for example, there's been times where you see Mammatus clouds like in the morning, and then later that afternoon, there are strong thunderstorms across the region. So Mammatus clouds are just kind of indicative of things to come, and that conditions are very unstable. So that's my comment about Mammatus clouds. Okay, so this is the last slide, you guys. You guys made it through. I only went 10 minutes over. Thank you for staying with me. I will go ahead and unmute you guys. And then you guys have to unmute yourself. And thank you guys for attending.